My name is Russ Lakis, engineer at Ophir Spirecon in Logan, Utah. We're going to be doing a webinar on understanding beam profiling calculations, their usage, and the results. In this module, we are going to identify many of the common beam profiling calculations. We will become familiar with the applications of different calculations, and we're also going to discuss a lot of the limitations of the calculations, different caveats that you need to be aware of. And then we'll discuss interpretation of a lot of the unintuitive results. When we're talking about a camera frame, we're talking about a two-dimensional frame of data of pixel intensity readouts captured by a CCD or CMOS camera. We use monochrome cameras only. So any of the images that you see that have a false color applied to them, that is not because it is a color camera. We apply a color palette in our beam gauge beam profiler that enables visualization of intensities across the dynamic range, so you can see those differences really well. Pixel readouts are generated by the electrical response of the sensor material. In this case, predominantly silicon, but there are other camera types as well. Background calibration we're going to talk about a lot. Background calibration is pretty critical to getting accurate beam profiling results. The reason is because the sensor readouts actually have natural electronic noise profiles which directly interferes with laser measurement. The electrical response of the sensor material can also change depending on the thermal environment. If it's hotter or cooler, then that electrical response changes. Also, if there are sources of ambient light in the environment where it's unavoidable and cannot be removed, you need to be able to calibrate that out as well. Any signal, whether it's thermal or electrical or ambient light, that all has to get removed, or otherwise it'll bias your measurement. In our beam gauge beam profiler, we offer the UltraCal calibration. This is the only patented background calibration algorithm for laser beam profiling. What UltraCal does is it samples the noise profile, preserving both positive and negative noise components, and then neutralizes the baseline, subtracts that frame out so that it can't contribute any bias. So we see in the frames to the right side of the screen, this is an uncalibrated frame. In beam gauge, we use a dark purple color to represent low-level signal and a gray color to indicate negative signal. So when we see this mottled gray and purple background, that is an even distribution of both positive and negative baseline components. We'll go into that in a little more detail in a future slide. For apertures, understanding software aperturing is important to accurate laser profiling. Beam gauge offers two different software apertures, and they can both be used together. Per the ISO specification 11146-1, aperture should always be applied to avoid bias from pixels outside of the area immediately surrounding the beam. This helps to be able to ensure an accurate measurement. The areas highlighted in red are going to be the pixels that are included in the measurement. It's just like drawing a fence around the pixels that you really want. The apertures should be centered on the beam centroid, as shown in these images. A couple important UI components of beam gauge as we go forward. We use the Microsoft Ribbon UI design. On the ribbon, you have tabs. Those are primary functionality groups. And then you have panels on a given ribbon that are a more specific group of functionality. We also have a results display where all of the different results are posted for viewing. There are a bunch of features tucked away in here, being able to enable statistics, pass-fail control, time charts, and also font and numerical formatting. You can also pull results off and make a floating copy on any of the other displays. Users can also use the C# programming language to make their own results, and beam gauge can pull those in, and the instructions for doing that are actually provided with the software download. So I want to jump right into the calculations. In beam gauge, we have a power and energy result group. These are all calculations which utilize measurements of pixel intensities to be able to characterize relative power measurements of a laser beam. Total or peak power, percent in aperture, or average power density, pulse power. These results can be displayed either in camera counts, just a pixel digitization, or you can also apply either a manual or a automatic power calibration from one of the Ophir power meters, and the results will be displayed in the appropriate units. So when we're talking about total power and energy, which will come up a lot tonight, we're talking about a cumulative sum of all pixel intensities in units of digital counts. This could be useful for understanding relative changes in beam power. Again, we can correlate that to live power sensor readings with an Ophir power meter connected via USB, or you can set a one-time manual power calibration. One useful way of using total power and energy is to monitor the baseline for like thermal drift or changes in that baseline. As you're using a CCD camera for beam profiling, it can change in temperature, and that does affect the measurements. Applying a new baseline calibration periodically and before any important measurement is definitely recommended. So in this case, we have enabled a small partition off in one unused corner of the camera frame, where we have our beam and our apertures enabled over here. Now, normally with a beam such as this, if you were not using apertures, the mass of all these pixels, the intensities of these millions of pixels would easily outweigh the laser. The laser signal is only a few 100,000 pixels versus millions. So that's partly why apertures are so important. A partition is a different type of aperture available in beam gauge. You enable this out in the corner, and then we can chart that and monitor the baseline calibration. Now, after an ultracal, if we've neutralized the baseline, we should see the electronic noise of the camera be equally distributed, both positive and negative. So we can see that the mean of this is right near zero, and that's exactly where we want it to be. What that means is only the real laser signal will be used in the calculation. In the chart at the bottom right, we see that the camera is drifting over time, and the response of those pixels is increasing. This is one useful way of using total power and energy. Peak power and energy is just simply the peak intensity of the laser signal. The maximum value is dependent on the sensor pixel bit depth. So for example, a 12-bit camera would be 4,096 counts. 14 bits, 16,384 counts, and so on. Ideal peak intensity for a laser, or for laser profiling, is to get the peak of the beam to in between about 70 and 95% of the maximum dynamic range. Too close to the maximum, and you're likely to reach saturation, and you're essentially losing data because you're unable to measure that intensity as you go off the top of what the sensor can measure. Too low, and you're too near the noise of the camera, and that starts increasing the uncertainty of your measurement. You can accurately profile lasers down to as little as 30% of the dynamic range, and in cases where you just can't get more laser signal, it's fine to do, but again, to decrease uncertainty, try and get the peak intensity to about 70 to 95%. The average power density result is the total power within the aperture divided by its cross-sectional area. Now, the cross-sectional area is displayed in the right-hand graphic here. This is the area inside of where the real measured beam width should be, and then on the left-hand side, this is just all of the pixels that are within the aperture. So we take the total power within the aperture and divide it by the cross-sectional area, and that will give us our average power density of that laser. Percent in aperture is simply the percentage of total power that is inside of the aperture versus the total power of the entire frame. And this is useful determining if all of the laser signal is actually being included in your measurement. This can also be used to spot whether or not the background is drifting or not. As the background drifts, either positive or negative, you'll start getting fluctuations in the percent of aperture result. Ideally, you want near 100% in aperture. For example, in this case, on the left-hand side, the pixels outside of the aperture are drifting negative. And you can see in beam gauge with the coloring that we apply, you can see this baseline is drifting a little bit gray. It's more predominantly gray than purple. In the center, it's balanced, and on the right-hand side, it's drifting towards purple, which means the baseline signal is drifting positive. So you can use that as a quick visual indicator to see whether or not you need to do a new baseline calibration as well. So a couple different options to be able to ensure that you do that. That's because it is such a critical part of the measurement. Next we have peak pulse power, and this is just simply the peak power energy in a single pulse. It requires a power and energy calibration to be enabled, either with a Ophir power meter or a manual power calibration, and then you also need to set the pulse width. That's done by the user. In a ribbon style interface, anytime that you have this little icon down in the corner of a panel on a ribbon, that enables an expansion dialog. And on the power energy panel, there is a dialog tucked away. These features aren't used all that often, but we will go over each of them today. And we need to enter the pulse width in microseconds into this field for this result to function. Otherwise, you will have a 0 result. Average pulse power is a time average power based on the pulse repetition rate in hertz. Again, this requires power energy calibration to be enabled, and also the pulse rate in hertz to be set by the user. Next, we're going to be talking about the spatial calculations. These are calculations which identify dimension, shape, or rotation of the beam signal, or locate features within that signal. These include calculations such as centroid or peak locations, ellipticity, eccentricity, and orientation, all off-axis mode results in beam gauge. These help define the shape and rotation of a non-circular beam, point-to-point linear measurement, and most importantly, beam widths. So we'll start with centroid. The centroid is the first moment or center of mass of all included pixel intensities. When we're talking about a geometrical centroid, it's simply the intersection of two lines of symmetry in an area, or the center of symmetry of an area. So in this case of a triangle, you see that the two lines of symmetry intersect, and your centroid is found here, there at point C. When we're looking at a laser beam, we'll see different effects, such as this low-lying signal that sweeps up towards the top of this beam causes the centroid, which is the point at where the dashed lines intersect. That is the cursor feature in beam gauge. You can see instead of being in the exact center of the green area, where one might expect it to be, all of this signal up towards the top of the beam pulls the centroid upward. In a spatial intensity profile, the mass or intensity of each pixel is considered such that the centroid can also be considered the center of gravity. For example, the balancing bird. The mass out on the wings pushes that out and allows it to still balance. So once we know where the centroid is, we can report its position, and we do that with an XY coordinate pair. We do that for both centroid and peak location. Those are found in the spatial results group. You can set the spatial units, microns, millimeters, centimeters, whatever you need, and that's found on the computations ribbon. The cursor and crosshair features in beam gauge can track centroid or peak. And in this beam, we have the centroid enabled. That's the dashed lines that intersect. That is the cursor feature. You can actually grab that and move that around, or set it to automatically track peak or centroid. The smaller reticle is the crosshair feature. And we give two different options for being able to track those positions depending on preference, and when they're both enabled, there are also some results where you can do linear measurement between the 2 points. Next up, we want to be able to talk about beam widths. And when we talk about beam widths, everyone wants to know what the right answer is. The best analogy I found is measuring the cotton ball with calipers. So if you visualize being handed a cotton ball and calipers and told to find the diameter of that cotton ball, it becomes very challenging. Where do you stop? What orientation do you hold the cotton ball or the caliper? So everyone wants to know which method is correct. There's a bunch of different beam width methods. They've surfaced over time in different industries. One of the best ways of understanding why there are so many, I like this XKCD comment. If we start with 14 competing standards, eventually we come along and say, you know what, we really need to solve having so many different standards. We end up creating a 15th standard. It's not without purpose. There are reasons for each method, and there are benefits to each, and there are drawbacks to each. Some beam width methods are more robust than other methods. Some are accepted as international standards, where we've started to come to agreement that this is a good way of performing the calculation. Some are preferred or created by different industries. Maybe cases where the accepted standard does not work well, so there's a preference for a different method. All beam width methods have scenarios where they may not perform well. All beam width methods improve in repeatability and accuracy if you take care to create optimal conditions. The idea is that we're trying to reduce uncertainty in the measurement. So no beam width method provides a one true answer. None of them are foolproof. They do require some knowledge and experience to use effectively. Before we talk about each method, we wanted to introduce the difference between beam widths and beam diameter. You'll notice if you've looked at beam gauge or competing products, there's both beam widths and beam diameter. Well, why would you use either of them? The answer is the diameter methods are intended to be used with circular symmetrical beams. There are often important mathematical distinctions between the diameter method and the width method. Even so, we see a lot of users just kind of use the XY widths in all cases, but there are different methods and different conditions where that is not the correct action. If you use the ellipticity result in beam gauge, you can make a determination of which you should use. To determine if your beam has circular symmetry, enable the ellipticity result, and if the result is greater than 0.87 or ISO 11146-3, then that beam can be considered circular and the diameter results ought to be used. First up is the 4 sigma or second moment method. This is defined as 4 times the standard deviation of the energy distribution. This is evaluated separately in the X and Y transverse directions over the entire 2-dimensional profile. In other words, the second moment method is integrating the energy over distance from the beam, the centroid of the beam, which obtains a properly weighted beam width according to beam propagation theory. It's the only method that actually does this, and so there are some big benefits computationally, and it impacts a lot of other calculations to be able to know that it does that correctly. The 4 sigma method is the most robust and reliable beam width method, as it does directly follow beam propagation theory. It is defined as an accepted standard in ISO 11145, 11146-1, and 11146-3. Other methods may be correlated to 4 sigma methods. There are different correction factors that can be applied to several methods to obtain a 4 sigma equivalent. A 4 sigma is also a necessary measurement method for accurate beam propagation measurement, m². There are separate calculations for 4 sigma for both the XY widths or the diameter results. Again, we want to determine if your beam is circular symmetric or not, and use the appropriate version of the result. I want to talk about the ISO standards for just a moment. In your particular application, you may not necessarily care whether a method is listed in the standard. Doesn't necessarily mean it's inherently more correct, but what it does mean is that it's a widely accepted method of calculating that result. And in all of our products at Ophir Spiricon, we do try to use the ISO standards whenever possible, and you will see that throughout our products. We always tag those results with a little ISO tag so you know how we're calculating it and can rely that is being calculated in a reliable way. Some of the problems with the 4 sigma method, it's the big drawback, well, not really drawback, the big weakness of the 4 sigma method is noise in the baseline signal. The 4 sigma method is sensitive to noise in the wings of the beam. It's less sensitive near the centroid or the peak, but noise out near the wings is definitely a problem. If there is positive noise in the wings, the resulting beam widths will be exaggerated, and vice versa. If it drifts negative, again, from a cooling effect or a poor baseline calibration, then the beam widths will be undermeasured. There are products that deal with the baseline by clipping the baseline away. Unfortunately, this doesn't actually correct the issue, as that noise profile is still applied to the beam signal, and just clipping the baseline away doesn't really get rid of it. It distorts the beam altogether and results in erroneous measurements. So quantifying the noise profile of the entire camera frame and then subtracting that out is the only correct way of dealing with that. I'm going to jump ahead to looking at a 4 sigma method and baseline calibration. So in this case, we were sent this file by a user. They had forgot to ultracal and were confused why their beam widths were so inflated. In beam gauge, we have a feature called a beam width indicator. That's the light green colored box that's being drawn around the beam. This is representative of the X and Y, or the major and minor beam widths. You can see in the minor axis of this line beam, the up and down direction, that beam width is substantially wider than the beam really is. It's also a bit longer as well, left to right in this image, longer than it ought to be. That's because we have that predominantly purple background where no calibration was applied. In this image, we characterized that baseline, created a post-processing reference subtraction frame, and then removed that from all of the data, even the beam. All of this had the subtraction frame removed from it. And we see that now the beam width indicator is snugging up a lot better to the beam. In the previous frame, we were about 4 millimeters wide in the minor axis, and now we're at about 1.7 millimeters, getting a much more accurate result. This beam still has a glow around it, and that still is going to affect the 4 sigma measurement. But if that's really part of the laser signal, then that would be appropriate. So there are other conditions that can cause degradation to a 4 sigma measurement. Different optical artifacts. We'll go over a few of those. One of the first is ancillary beam reflections, or ghost beams, as they're sometimes called. If those reflections are aligned with the beam you're trying to measure, it can cause fluctuations and interference with the primary laser, and it'll cause your results to be incorrect. So you want to make sure that you and move these beams away from your beam. So long as they're moved off, they're not going to affect your beam measurement. And in this image, these ghosts are very light. That's because I've already applied attenuation to reduce those ghost beams to the point where they're not going to affect the beam I'm trying to measure in a statistically significant way. Lasers can often have a glow around them. Sometimes it's just because it's not quite Gaussian and some of that energy is distributed out towards the wings of the beam. Sometimes it's by sources that you're not trying to measure, such as a flash lamp, the ambient environment. In those cases, you want to make an effort to identify if the halo around your beam is real or not and try and remove it if it should not be there. If it's part of your laser signal, then it's okay to profile that because that will have an important effect on your resulting measurement. Physical apertures like pinholes to exclude the signal and remove that from the measurement. Blooming is a radial artifact in some silicon sensors when used in the NIR range above, starting at about 1030 nanometers to about 1090 nanometers. And it's typically caused by a type of pixel crosstalk and isn't really correctable. It's usually is an issue that is detrimental to the measurement, and effectively that camera is not going to be great at measuring beams in the NIR. And to detect that, we can use an in-gas sensor that's impervious to that effect. So we can see this is the same beam in the same orientation and the same sensor location in both cases. And we can see this in-gas camera did not detect that blooming effect around the beam, so we know that that is an artificial effect caused by the camera. One that's a little more common is called CCD smearing. This is a vertical band that you'll see co-located with the laser spot. And this effect is caused by CCD design and occurs when silicon CCD sensors are used in the NIR. And this occurs due to low responsivity of the silicon in the NIR band. It requires a lot more laser energy to excite the sensor. And while the sensor isn't generating signal, that laser signal is affecting the sensor in other ways. And it causes the vertical shift registers in the CCD design to overflow. Those are all their vertical shift registers, and it cascades up and causes this smear up and down the frame. And that will move, if you move your beam left to right, it will move with it. This can be mitigated by increasing attenuation and then increasing the camera exposure time of the camera. This causes less energy to be contacting the sensor and reducing that effect. In cases where that is not able to be done, beam gauge does have an anti-smear feature which will characterize the smear near the top and bottom of the frame and then subtract that from your beam. But if you can avoid it from being a problem in the first place by reducing the laser power, that's definitely preferred. Next up, we have the knife edge beam width method. This result is the distance between 2 points on the measured profile that are equal to a percentage clip level of the maximum power. This method encompasses a fixed fraction of beam power independent of the modal structure of the beam. It's performed using an X and Y 1D data set. So you don't really consider the rest of the data except for those 2 slices. The knife edge method does require a user input multiplier, which is then applied to the measurement, which allows it to correlate to other methods more accurate or more realistic width. So to do this calculation, the beam is effectively sliced with a knife edge. It can be physically done with essentially a razor blade, and that's where the knife edge comes from. But in software, we can just step in on the columns and the rows and perform the same measurement. Some of the most popular clip levels are 10% and 90%, and 16% and 84%. While ISO 11146-3 does recommend 16% and 84%, At SpireCon, we found that the 1090 clip levels have a better accuracy under a larger variety of situations. And we've correlated that with a paper by Sigmund, Sasnet, and Johnston, where they looked at the knife edge clip levels under a variety of conditions, different beam types, top hats, circular beams, line beams, and recommended different clip levels based on their findings in that paper. So we would recommend the 1090, but we provide both and then the option to define your own. So some of the limitations of this method are that the user must apply a knife edge multiplier that depends on the base modal content. And by the base modal content, saying if you have a square top hat, you would need a different multiplier than a round top hat. If you're measuring a Gaussian beam, you have a different multiplier that you should use for that as well. And one of the issues that can arise with the knife edge method is using the inappropriate multiplier and not knowing that that multiplier needs to be changed for the type of beam, which can invalidate your results. Multipliers from a few different standards. Multiply is different from some of the standard multipliers, do require a little bit of a learning curve, and referencing some clip level plots. Again, I recommend Siegmund's paper on clip levels and referencing those plots, and you can find the one that's appropriate in your case. The knife edge method can inherently have systematic errors as the mode mix of your laser changes from Gaussian, and it won't necessarily consider that. Again, it's using two orthogonal 1D data sets versus the two-dimensional data set. Next up, we have the percentage of peak power. This is the distance between 2 points on the distribution determined by a selected clip level. This is measured again in two orthogonal data sets, like an X and Y 1D profile. That is set at the centroid location, not the peak location. You're basing the clip level off of the peak, but the placement and selection of the data is off of the centroid location. If two or more points fall to the clip level, the closest to the peak are selected. And there are different ways of doing this measurement. You can start at the peak and work your way down, or the highest value, which may not be the peak. You can work from the outside in, or you can tally all of the pixels that cross the clip level and then multiply that to find your width, which is a more robust approach that is used by beam gauge. Some of the more popular clip levels are 13.5%, which is also referred to as the 1 over e squared method. 1 over e squared does provide an important correlation to Gaussian beam mathematics. 50% of peak is also very popular and is termed full width half max. If you are doing full width half max measurements, you can correlate those measurements to 1 over e squared by multiplying that beam width by 1.699. That's a constant multiplier that can be used. Some of the limitations of the percentage of peak is that it does only use the two 1D profiles, so one row, one column of data intersecting the centroid. The limited data set doesn't really consider the full modal content and distribution in the beam. Because of this, it does work better on symmetrical beams, such as like a single mode laser. As the modal content, you get higher order modes in the beam, then you can start to get some unusual or unexpected outputs from this calculation. One of the other problems is if you have not just a single peak, but you have a lot of variation, such as in a top hat beam where there's a plateau of many small peaks, the results can get a little erratic as well. This method is definitely less susceptible to noise than 4 sigma, but does not have industry traceable results for beams other than TEM00 diameters. Mixed mode results are not particularly meaningful, except in the terms of user-defined context, and by that we mean per application. In a higher order mode beam, you can still use percentage of peak, but the exact meaning and reliability of that measurement is up to you to determine. So this is a really good case for one of the limitations of percentage of peak. When we have many small peaks, such as in the long axis of this line beam, depending on where your clip level is set, you may actually trigger, you may cross your clip level at unexpected locations. And also your peak and centroid locations are not co-located, meaning the peak intensity that your clip level is going to be referencing and the distribution at the centroid may not be equivalent to each other. That can cause some unexpected issues as well. Not every beam width measurement and beam width method can be used in all cases. And sometimes we see users that are very stuck on using a particular method, even though the laser that they're using and the rest of the signal, their application, isn't going to really support that measurement well. And there are alternate methods which will get a very similar or will have good correlation to what they're trying to do, but they're kind of stuck on using this one method. We would recommend against doing that. There's many methods, and you should use their strengths and weaknesses appropriately. Next up, we have the percentage of total power. When we're talking about power, it's always power or energy, depending on whether you're CW or pulsed. Percentage of total beam width results is the width of all of the pixels which exceed a clip level of total power. There are two methods for this result, depending on whether you need the widths or the diameter. So for the widths, we're looking at two orthogonal lines of data which intersect at the beam centroid, and it's the width of all of the pixels which exceed that clip level. So you tally up all of the pixels that pass along those two 1D data sets, multiply it by your pixel width, and that gets you your beam width. For the diameter result, for a circular symmetrical beam, the diameter is the area of all pixels which exceed the clip level in that two-dimensional area. 86.5% is the most widely accepted clip level, and while you can use other clip levels, that's predominantly the one that is used. Again, we see a limitation of using just 1D orthogonal data sets. The limited data set may not properly consider the modal content of your beam, and this definitely works better on a symmetrical beam rather than an asymmetric and mixed mode beams. Total power, percentage of total power method really shouldn't be used on a donut TEM01 star distribution. You can see with the we have 4 sigma measurements along the top for both the X, Y, and then diameter measurements. And at the bottom we have the percent total, X, Y, and diameter. The X and Y measurements are clear off by about 20 microns. This is because that dip down to near baseline levels in the center really mess with those width measurements. Really can't be used at all. The diameter measurement, because it is counting all of the pixels in the two-dimensional area, does get it a little bit closer, but still misses the mark percent. Next up, we have the moving slit method. Moving slit is an equivalency to a scanning slit laser profiler, such as we do have a nanoscan product. The nanoscan is a scanning slit profiler. That product uses a rotating drum with a metal slit. Those slits allow a small portion of laser signal through to a sensor back behind it and allows you to map out where the laser intensity is. So in a moving slit method done on a CCD, you are looking at the rows and columns of data and summing that data. So for this method, the first thing we do is we sum all of the intensities for every column, record those sums, and then do the same thing for every row. We end up with 2 one-dimensional data sets. Based on those one-dimensional data sets, then we can do a 1/e² percent of peak beam width measurement. The summing includes all of the beam structure, but does disregard the spatial distribution, the original distribution of where that power was. And that can cause some unusual issues. For example, both a nanoscan scanning slit device and a camera using the moving slit method are sensitive to rotation of the device to the beam. We want to apply a rotational correction and align that device to the major axis of the laser to get consistent results. One of the big limitations of the moving slit method and scanning slit devices in general, they're not wrong, it's just there are complications with it. And the difference comes between the types of 1D profiles that are generated. A pixelated sensor, such as a CCD, produces what we would call a spatial energy profile. A scanning slit device, and also the moving slit method, produces a summed energy profile. The two different types of profiles, the data turns out to not be equivalent except in the cases of TEM00 Gaussian or TEM01 star donut beam. As higher order modes are introduced, the profiles start to diverge and will not result to the same 1/e² measurement. So in this case here, we're taking a just 31 pixel by 31 pixel data set, and it is somewhat Gaussian of a laser. Now in the top plots, we have the X centroid data and the Y centroid data. So that is the row and column in the frame all the way up and down and then side to side, that row and column. Those are the two top plots. Then we've taken all of the summed data. We have the sum distribution. And you should be able to see that even between these two, we have a near Gaussian beam, small data set, and there are still differences in that distribution. With a higher mode and a lot more data, you get a lot more variation in the measurement. So if you are doing any sort of comparison, if you've been using a scanning slit profile and want to go to a camera-based system, this is a really important distinction to understand, that the two are not necessarily comparable. You have to be very careful about how you compare those two sets of results. Next up, we have the encircled power methods. There are two different methods: the encircled power smallest aperture, or EPSA, then encircled power smallest slit. EPSA is a diameter measurement, the diameter of a circle that encompasses a given percentage of the total beam power. So you start with a large aperture and you decrease its size over and over, trying to find the smallest aperture possible that then encompasses 86.5% of the total beam power. 86.5 is the clip level that is defined by ISO 11145. That variation is provided in beam gauge. D86, an 86% of total power, is also a common method and uses the same technique. You'll often find reference to it just as D86. The ISO version, 86.5, is what we provide in EPSS is a width measurement. It provides X and Y widths. Is the smallest width of an adjustable slit. You center the slits on the centroid and then reduce those slits down until it contains 95.4% of the total beam power. Again, that's an ISO measurement defined in 11145. That's provided in beam gauge as well. The encircled power methods do have some limitations. They are less susceptible to 4 sigma or to noise than 4 sigma, but there are not industry traceable results for beams other than the circular or elliptical, near TEM00 beams. Mixed mode results may not be particularly meaningful, except for a custom application where you've been able to characterize what those results mean in your application. For a TEM00 beam, both of these methods will return accurate second moment diameters. So in a case where you can't really get rid of noise near the wings and the force sigma is, blowing up a little bit, these methods can be a good alternative. But as the mode content increases, both of these methods result in a degraded measurement from ideal. Is nanoscan only good for a TEM00 beam? No. It's just you need to be careful. Any of the beam width methods that use an orthogonal data set, just the 1D profiles, you need to be careful about what you're doing. You should ensure that you've rotated to the major width of the beam. That way you're getting a consistent result. If you're, aren't careful in setting it up and you're not consistent in the way that you perform the calculations, that adds a large amount of uncertainty into the measurement, and you'll see a lot of unexpected results. So consistency is a big key, just how you set it up, where you rotate to. If you're changing where you are in propagation, the major axis might shift. You'll want to make sure that you align to those axes. When you have higher mode content, it still provides good results, but it does increase the uncertainty because it doesn't really consider the rest of that. Going into divergence results, there's only a few in this category, and 3 of them are all divergence angles. There's the theta major, theta minor, and theta result. The theta major and theta minor are calculated for non-circular beams, and theta can be used for circular symmetrical beams. And that distinction all the way through is present through many of the results. Divergence measurements that relate to beam propagation theory are always based on second moment beam widths. If you're using let's say a 1 over e squared beam width and trying to calculate divergence, you're going to see some unusual or unexpected results in your divergence measurement. So we always recommend that you set the beam width basis setting in beam gauge to a 4 sigma or equivalent second moment width when you're trying to perform divergence calculations. A limitation for the divergence angle measurements. Using these, we're going to talk about 3 different divergence calculations that are available in beam gauge. There are different test methods. Anytime you're using anything but 4 sigma as the basis will require you to verify those measurements for your own purpose. So the first of the divergence methods available in beam gauge is the ISO focal length method. It's a simple and effective method. We calculate the far field divergence at any point in the beam propagation path. And you do this by placing a known lens into the beam path and then putting the sensor of the camera at the precise focal length. You'll need the ability to know that focal length well and both place the sensor in the correct location. Then all you have to do is enter that precise focal length into the beam gauge divergence panel, just shown here. This is on the computations ribbon. This is the divergence panel. You do that, and then the divergence calculations are automatically calculated and displayed in the results display. Some of the limitations are that the optic that you use needs to be suitable for the application. It can't be diffraction limited for the source that you're using. And if you're not making those considerations, you again may end up with pre-uncertainty in your result. The next method is the far field wind angle method. And this is the same control panel in beam gauge. Select from all 3 methods, same panel, and the controls will update to the correct one. The far field wind angle method is useful for measuring divergence of devices like laser diodes. The divergence angles tend to be quite large and are usually measured in degrees. Typically, it's an industry standard change in that regard. All you have to do is know the distance, measure the physical distance from the device that's being tested and the sensor of the camera. Enter that distance into the control in the divergence panel, and the divergence measurements are automatically calculated. Care needs to be taken to not overfill the detector, or the results are invalid. If you're not capturing all of the signal, then obviously it's not a valid measurement. So if a source is not circular, then the y-axis of that source should be aligned with the y-axis of the sensor. The third divergence method is the far-field two-point method. The two-point method uses an empirical test comparing beam widths at two different locations in the propagation path and calculates the resulting divergence. To do this test, you place the camera in the propagation path, in the z-axis at a location. It doesn't even have to be a specific location. Press the check mark button in the divergence panel, and all of the current beam widths will be put and preserved into the panel. Then translate the camera, move it in the z-axis, record the precise distance traveled, enter that into the divergence panel, and then the resulting divergence measurements will automatically be calculated. For this mode, we definitely recommend that the 4 sigma method is your beam width basis. Also, this method is sensitive to angular rotation. You should disable the off-axis mode in beam gauge, which occurs automatically if you turn off off-axis calculations such as orientation, eccentricity, or ellipticity. Those 3 results, if they are turned off, then beam gauge is in an XY laboratory coordinate mode. You turn those on, then it turns to a major-minor rotational mode. The last result we have in the divergence category is called radiant intensity. This is the average power per steradian that is contained within a second moment beam width. So we do a first pass, measure the beam. Once we know the beam width, then you can compute the average power that is within that entire area. Once the far field divergence is known, then radiant intensity is able to be calculated, and that is consistent independent of position in the propagation path. The test to do this is done by placing the sensor at the focal length of the lens. So this calculation can be done very easily at the same time as the ISO focal length divergence method, the first of the 3 that we talked about. Both of those results, as you're moving the CCD sensor into the focus of a lens, you should be very careful to ensure that the focused power is below the damage threshold of the sensor. Otherwise, you will burn the sensor and it will need that sensor replaced. Most of the results in the Gaussian groups, beam gauge has both a set of 1D Gaussian fit results and also 2D Gaussian fit results. Both result groups already provide many of the previous results that we've talked about, except they're computed from Gaussian fit curves instead of the raw beam data. So while they have different names, functionally they're equivalent, so we really only need to cover them briefly. For example, Gaussian height is simply the peak intensity of the Gauss fit of the raw beam data. Gauss widths, x and y, are simply the second moment widths of the Gaussian fit, both 1D and 2D. The delta centroid x and y, instead of just calculating a centroid, we calculate the delta between the input beam centroid and the Gaussian fit centroid. In the 2D Gaussian results, we use a 2D whole beam Gaussian fit, which is performed via the least squares fit. The 1D Gaussian fits just use orthogonal row and column data just from the cursor in beam gauge. It's the dashed line that goes all the way through both axes. All the 1D Gaussian fit results just use that 1D cursor data. So for full descriptions and differences between the 1D results and the 2D results, visit the beam gauge user guide, section 5.19, and there are tables which discuss each of the differences between those, but the differences are fairly minor. There are 2 results left in the Gaussian groups that we need to talk about. They're both were at one time in the ISO specification. Both were introduced in ISO 13694 in the year 2000. both have since been removed. So goodness of fit is a parameter based on a popular statistical test which characterizes the fit between the measured distribution and a theoretical distribution. It measures how close the two distributions are to each other. The result is a value between 0 and 1, where the quality of the fit improves as the result gets closer to 1. So it is important to note that that definition was removed in 2005. This equation was found to be sensitive to variations in the number of samples. Depending on how you calculate it and how many samples, you can end up with results that are potentially difficult to interpret. If in one case you used 1,000 samples, in another case you used 1,200 samples, the result might not be comparable to each other. And it could be a little confusing on how to interpret that. Again, consistency of the measurement is key. In general, doing all of your measurements consistently is a key to be able to understand those results the easiest. We leave these results both in our nanoscan scanning slit profiler and our beam gauge camera-based profiler, because we do have a lot of users that use these calculations. They believe they've found reliable uses for them. So we make that, we let you to make that determination for yourselves if that's a useful measurement or not. Similarly, the roughness of fit calculation from ISO 13694. The roughness of fit was left in until 2015, as it has some similar possibilities where it may be difficult to interpret. But again, we've left that in both of our products. I'll let you make the determination for yourself. The roughness of fit calculation is the maximum deviation of the theoretical fit to the measured distribution. So the goodness of fit was dealing with characterization of two fits, and the roughness of fit is directly comparing the deviation of a theoretical fit to the measured distribution. Very similar. In this case, the roughness of fit value, again, is between 0 and 1, but as the fit improves, the value approaches 0. So the last group that we have to cover is top hat results. If you're working with top hat lasers, this is the category that you're going to care about the very most. The top hat results all characterize top hat beams or top hat-like distributions, where the sides of the beam are much more vertical than a Gaussian distribution. The top is very flat. All of these results in this group are from ISO 13694. And beam gauge, similar to the Gaussian group, there is both a 1D version and a 2D version of these results, with some differences between them. Refer to the beam gauge user manual for those differences. First, we have flatness factor. Flatness factor is defined by ISO as the ratio of the effective average power density to the maximum power density at a given Z location. It's just simply you find the average power density of the entire distribution, and that's your lower point, your peak power density, and calculate the ratio between those. It's going to be a value between 0 and 1, where a distribution with a perfect flat top, perfect straight sides, perfectly flat top equals 1. The effective irradiation area is the irradiation area in which the power density exceeds the threshold density, which is the threshold density is a selected fraction of the maximum power density. And in other words, it's a clip level that you choose. There are no standard threshold density values, whereas in the beam widths, there's some very common ones that are used. ISO does not define any standard threshold density values. So some of the limitations are that the threshold density is a clip level that is dictated by the user depending on the application and a bunch of potential other factors, all of which are likely different for every application. So interpreting these results between two different applications can be difficult. Again, consistency can be key in obtaining measurements that are easily interpreted across applications. To set the threshold density, there's an expansion dialog on the power energy panel in beam gauge on the computations ribbon. So until you set the threshold power density, either a percentage value or a digitization level, you'll find that some of these top hat results will not have any values calculated for them. The effective power, or the effective energy, is a measure of the power contained in an area of pixels which exceed the threshold fluence, or the threshold value that we mentioned in the last slide. This characterizes the area of the beam which is contributing to that top hat profile. So in the plot, this slide, all of the beam signal that is above this threshold, we considered that anything above 70% is really contributing to the work that laser is doing. Then all of the energy that's falling below that is insufficient to do the work. So for example, if you were trying to measure the effect power for a laser that's doing ablating, then you may know that if it falls below a certain threshold, it's not going to be powerful enough to ablate effectively. So in this case, you could set a threshold value that makes sense for your application and determine how much of the beam is really doing the work to the level that you need. Along that, right along with that result, with effective power energy, we have fractional power and energy, very much related. This is a fraction of the effective power to the total power in the distribution. So if all of the top hat qualifies as being intense enough to do the work, then that would be a perfectly flat-topped beam. All of it crosses that threshold, and the result would be equal to 1. Next, we have the effective average fluence. This is a spatially averaged power density defined as a weighted mean, and this is just the weighted average of the distribution in the plateau of the top hat. Next, we have beam uniformity. This is one of 3 calculations that attempt to describe the top of the top hat. We have flatness factor that we've covered first. Beam uniformity interprets the top of the top hat as the normalized RMS deviation of the power energy density compared to its average value. And if it's a perfect flat top beam, the result would be equal to 0. That would be perfect flat top with perfectly vertical edges, and then it moves away from 0 as that degrades. The third result, which characterizes the top of a top hat, would be plateau uniformity. This is probably the one that I see used most often. This is defined in ISO 13694, and it's a really good method. It does a good job, and it seems like it's intuitive at first glance, but it turns out it's not. It's kind of a confusing result in the way that you calculate it. Sometimes we see a lot of confusion from people that are using this, where they thought it was doing one thing and it's really calculated much differently. Plateau uniformity characterizes the maximum deviations of the plateau. The result becomes closer to 0. It approaches 0 as distributions are more flat-topped. This result talks about a full width half max measurement. It says delta E sub full width half max is the full width half max of the profile peak. In this case, it is not actually talking about the raw beam data. It's not the profile that it's talking about. It's the profile peak near the maximum of the power energy density histogram. And that distinction is very important. So in doing this calculation, you need to take a histogram first of the beam profile data, and then you do a full width half max calculation on just the plateau data in the histogram. So in the histogram, all of the bins from the sides of the beam the baseline data, all of that, and all we care about is just the bins that comprise the plateau itself, top of the top hat beam. And based on how many bins, or the full width, half max width, that cross that 50% threshold, characterizes how wide the deviation of the plateau is. I'm hoping that makes sense. Again, it's not a very intuitive thing. We actually do have this broken down in a step-by-step presentation. You are trying to do top hat characterization and have looked at plateau uniformity, go ahead and give us an email and we can work with you on understanding how that works a lot better. Perfect top hat beam would have all of the plateau intensities, everything in this histogram, falling into just a single bin, which is why the result would then approximate 0. It may not be intuitive at first, but we have this in a step-by-step guide, and which helps you better understand and interpret these results for real top hat lasers. The last of the top hat results is edge steepness. This is an alternative way of measuring the verticality of the edges of a top hat distribution. It uses a normalized difference between two different areas, one at 10% intensity, 10% of the power density, and one at 90% of the power density. So if the area at 90% is quite equivalent to the area at 10%, that indicates that the edges are vertical. They're straight up and down. Those areas were not very different. There is a frame info results group in BeamGauge, and this is just simply frame metadata, which is used in many of the calculations. There's really no special calculations or behind the scenes magic for how any of these values are derived, and they can be useful in your own calculations and helping determine different factors of your own application. That is all I have for you today. Consistency is key. Background calibration is incredibly important, and if you're having any troubles, please reach out to us.